Hello, everyone. How are we doing? Can you all hear me okay? Well done, as always, for having the motivation to get some physics done on a Sunday. Hey, Magdalena, how's it going? Hey, Ash. Hey, Astra. Hey, Dahlia. Hey, Idris. All right, so have you guys learned about heat and temperature before, or is it the first time seeing this kind of stuff? Either answer is fine. Okay, you hear me. Awesome. First time. Nice. Okay. Cool. You've learned it before. Okay, sweet. Well, the way this will work is you can stop me at any point and just ask any questions you have, and I'll do my best to answer them. So anything you're confused about, just pop it in the chat. Feel free to guess along with the things I'm saying. I'll probably ask random questions as well, so feel free to try and pop the answer in the chat if you can. It doesn't matter at all if you get it wrong. In fact, it's great news if you get it wrong, because then we know what extra stuff to teach and so on. So yeah, take a punt at anything I ask if you feel like it. This is second year for, I think, all exam boards. Yeah, it's year 13, so second year. All right. Yeah, I'm doing well, thanks. I hope you're doing well too. Okay, let's do this, shall we? Let's get started. All right, so about me first. If this is your first time here, my name is Matt. I'm head of physics at SnapRevise, currently doing a physics PhD, and I've been tutoring this A-level syllabus for quite a long time now. Looking forward to going through a bit of it with you today. So just as a heads up, it's the start of a new term, and we've got all sorts of courses on the SnapRevise website, and everything is 25% off at the moment. So if you go on the SnapRevise website and you want to see more videos like this and some more tailored courses as well, exam board specific ones, you can use this code back to school 21 and you'll get 25% off. Awesome. So in the meantime, let's get ourselves started and actually do some physics. So our objectives today are all about heat and temperature. So we're going to learn what heat and temperature are. We're going to learn what internal energy of a substance is, which is going to have a lot to do with heat and temperature. We're going to understand why it is that scientists often don't use the centigrade temperature scale. They often don't measure temperatures as so many degrees centigrade. They measure them as so many degrees Kelvin. And there's a really good reason for that, and it's all about what's called absolute zero. Finally, we're going to calculate and describe various changes to a substance when it's heated. So if you've seen this stuff before, that last point is all about specific latent heat and specific heat capacity. All right. So I'm going to go over, before we start the proper lesson, I'm going to summarize and go over a couple of things that are just worth having in the back of your head as the kind of background context for this session. All right, so the first thing we want to know about is melting and freezing points. So can anyone tell me, what is melting? Can anyone describe kind of in physics words, what's melting? It's some kind of a transition, I'll tell you that much. But what's it a transition between? When things melt, they start as something and finish as something else. So an example would be like ice to water, for example. Yeah, exactly right. It's a change of state from something which is solid to something which is liquid. Good. So for example, that would be like ice turning into what we typically call water, by which we mean liquid water. Nice, okay. And this happens to happen here at 0 degrees centigrade, but for a different substance, for like a lead or something, the melting point would be a different temperature. Good, absolutely right, solid to liquid. Okay, so then what's boiling? Boiling is also a transition. It's a kind of higher temperature one. For water, it's kind of the transition between like a liquid water and I guess what we would call steam. And it happens at 100 degrees centigrade. So that is the kind of mechanism going on underneath, and we're going to talk about that. But right now, we're just talking like very large scale. Boiling is just going from a liquid to a gas. How that happens, we will talk about today. And you're right, it is all about breaking into molecular forces. You might see that as well if you're doing chemistry. I know it comes up there too. All right, next, we're going to talk about two types of energy, which are really important when we're talking about temperatures and states of materials. So the first type of energy is the energy that you associate to the motion of something. So if something's moving, it has kinetic energy. The energy due, and does anyone know the formula for this? Due to motion. We won't actually need the formula for today, but just to help you recognize it, it's the one that's given by a half mv squared. So if you have a bigger velocity, v is bigger, so v squared is bigger, so your kinetic energy is bigger. More motion, more energy. Good. And then there's potential energy. And this is a bit more abstract. Motion, we're kind of pretty familiar with. Potential energy is energy due to a non-contact force. There's lots of ways of defining it. That's the one we're going to use here. The idea we're kind of capturing is we're putting a couple of different things into one here. For example, there's gravitational potential energy, where you have maybe the Earth and the Moon. They're not in contact, but they are exerting forces on each other. In particular, the forces due to gravity. So they're exerting non-contact forces on each other. And as a result, there's some kind of an energy. There's some kind of there's a pull that's going to make each of these things want to move. And that's measured by its potential energy. Okay. So often when you move around, like here, you can trade things like your potential energy that you have from being so far away from the Earth, move a bit closer and gain some kinetic energy. So these two types of energy can get converted into each other. Another type of non-contact force is a kind of intermolecular force. You have two particles in some kind of a molecule, or two molecules in some kind of a substance, and they have some kind of a bond between them, which is quite often some kind of non-contact force that's attracting them together. In fact, that's the kind of force that's going to come up today. So whenever you have bonds, you have potential energy. Okay, so here's the spec points we're going through. As you can see, it says A level only, so it really is second year. Here it's module 5, which I'm pretty sure is second year for OCR, and topic 9 again for Excel. Great. Okay, so we're going to start with the conceptual stuff in the first half of the session. So we'll do the conceptual stuff, then we'll do a question on that, and then we'll do the kind of more mathematical stuff. All right, so first of all, internal energy and temperature. So can anyone tell me what the internal energy of a substance is? If you've never seen this before, I think there's no way you could know this, but feel free to have a guess as well. So I'll start writing it, but I'll leave some gaps. The internal energy of a substance, and it's given the symbol U, is the sum of the randomly distributed, okay, so we'll come back to that soon, something and something energies in a substance. Okay, so there's a bit to unpack here and a bit to fill in. You're right, it's the kinetic and potential energies. So let's write that in and then see what it means. Kinetic and potential. Okay, so here's the idea. Let's imagine I have some box, I think, or some container. I think maybe liquid is easiest to think about to start with here. So here's a liquid. And if you were to look at a liquid under the strongest possible microscope, what you'd see is essentially a load of molecules. And they're all moving around. The liquid looks still when it's there in a container. If you zoomed in and looked at the particles it's made of, they're all going around like crazy. So there's all these particles, molecules, they're moving around. So they have some kinetic energy. So, and because they're moving around all the time, we can't keep track of where they are. So we just assume these kinetic energies are randomly distributed around the liquid. Okay, so then what about potential energies? Well, liquids are not gases. And the kind of difference between liquids and gases is that the particles are being held quite close together. Now, them being held quite close together, that shows that that's essentially there's some kind of attraction or force between all the particles. And as a result of that force, they all have potential energy. Again, different particles in different places have different amounts of potential energy with respect to different forces. So we just assume all of these energies are randomly distributed. But the point is there's two types of energy in this substance. There's this potential energy because the particles are attracted to each other. And there's this kinetic energy because all the particles are moving. Add them all together, and we call that the internal energy. Okay. So we can increase the internal energy by either supplying heat. So if we just put a flame under our liquid, essentially we give all the particles in the liquid more energy, so they start moving faster, or maybe they get enough energy to break away from each other, which would change their potential energy. So we can supply heat, or more abstractly, and we won't worry about this so much today, or doing work. And you'll see more about that bit when you do kinetic theory. Okay. Similarly, we can decrease internal energy by removing heat or letting the substance do work. And again, you'll see more about that in kinetic theory. Okay, so let's just take a closer look at these three different states of matter that we care about. There's solid, liquid, and gas. And these are the most common states of matter and the ones you need to know about at A level. So we can talk about how much of each type of energy each of these states of matter will have. So let's imagine this is water. So we've got ice here. We've got, I guess, like liquid water here, what we often just call water, and then steam here. So increasing the temperature will also increase the kinetic energy. Yes, absolutely right. In fact, temperature essentially is internal kinetic energy. So you're absolutely right. Increasing the kinetic energy increases the temperature, or if you like, increasing the temperature increases the kinetic energy. Good. Okay. So let's look at these three states of matter. Solids, the particles don't even have much room to move around, and they don't move around very much. So they have low kinetic energies. Now, also, they haven't broken apart from each other. They're very tightly bonded. And this might be a bit less intuitive, but that actually means they have low potential energies. Essentially, your potential energy is bigger the more of a bond you've managed to break. Okay. Liquids have a kind of, well, let's talk about gases. Gases have high kinetic energy. They're moving around fast, and a high potential energy because they've all broken their bonds. Liquids are in the middle. Mid potential energy. Okay, good. So in a solid in particular, one thing I want to point out is essentially you've got a grid. These particles aren't free to move around or move past each other. They're in what we call a kind of a lattice. And The only movement they can do, because they can't move past each other, is just kind of vibrating on the various spots where they live. So they just kind of shake backwards and forwards, but don't move around each other. Okay, so that's all we need to know about internal energy. And then you're asking about temperature. And there's actually a lot of interesting stuff to say about temperature. So let's do some of that now. So let's say we kind of know what temperature is, in the sense that we have thermometers and we've gone around and measured the temperatures of various things, throughout our lives. Now, it turns out if two objects in contact have what turns out to be what we call the same temperature, then what this really means is they are in what we call thermal equilibrium. So you're probably familiar that if you have one object which is kind of hot and the other which is cold, then after a while the hot thing starts to transfer its heat to the cold thing. However, if both of these objects have the same temperature T, then because one isn't hotter than the other, heat can't flow from A to B or from B to A. They just stay the same. Neither can heat the other up. And that state between these two objects is what we call being in thermal equilibrium. No heat goes from one to the other or the other way around. Okay. So next, we're going to think about the thing that actually was said in the comments. Increasing the temperature increases the kinetic energy. Absolutely right. So temperature, how hot something is, that's about essentially how fast the particles are moving. What's interesting about that, and what's a bit weird about the centigrade scale, is in 0 degrees centigrade, well, there it's pretty cold, so the particles aren't going to be moving around very much, but they will still be moving around. And you can get to more negative temperatures. You could get to minus 100 degrees centigrade or even further. So what we really want is a new scale of temperature where 0 temperature means that the particles aren't moving. We know the particles slow down as we decrease the temperature. We want 0 temperature to be 0 motion. So this is what we're going to call absolute zero. Absolute zero is the temperature when particles have no kinetic energy and, as an extra technical detail, and minimum potential energy. Don't need to worry about that part so much. Okay. So I don't know if anyone knows what absolute zero is, like what it is in degrees centigrade. How cold is absolute zero? This is the great thing. It doesn't depend on the substance. Absolute zero is just absolute zero. It's just one number that we define, and it's minus 273.15. Absolutely right. So if I plot something like my kinetic energy against temperature, then as we said, let's say this was in degrees centigrade. At 0 degrees centigrade, we still have some kinetic energy, but at minus 273.15 degrees, we have 0 kinetic energy. And so this is the temperature that we're going to call absolute zero. Okay, great. So if you want to know, yeah, good, absolutely right. So now what we're going to do is define a new temperature scale whose units are called kelvins. So you can ask, how many kelvins is my temperature? And the idea is that 0 kelvins should be minus 273.15 degrees centigrade. So there's an easier formula for converting between the two. Essentially, the temperature of something in Kelvin is given by its temperature in degrees centigrade plus 273.15 degrees. Okay. So the absolute zero scale for temperature is measured in kelvins, or Kelvin. Okay, good. And this is how you figure out your temperature in Kelvin. So for example, 5 degrees centigrade would be equal to 5 plus 273.15 kelvins. So that would be 278.15 kelvins. Okay, how is everyone feeling? Does anyone have any questions? Hey, Bose Academy. So yeah, does anyone have any questions? How are we feeling? Was this straightforward? Is it all right? Are we confused? Do let me know if you have any questions. Okay, nice. Definitely, yeah. All right, sounds great. Let's do some questions to check how it's going. So 6A, describe the motion of atoms in a solid at a temperature well below its melting point. Okay, so let's draw ourselves a picture. We've got atoms in some kind of a solid well below its melting point. Now that was when they were all together in some kind of a grid, or actually I used the word lattice, you might remember. And that's quite a nice word to use. So the atoms in a solid are held together in a lattice. Each atom vibrates around its position in the lattice. So what we've managed to get across in this sentence is the fact that the atoms in this solid aren't actually moving past each other. They're just in fixed places. Good, really nice. So this is a really nice question, the second one. What is the effect of increasing the temperature on the motion of these atoms? So this was actually mentioned in the comments. So let's say I take this solid and I start to heat it up. I put some kind of a flame underneath maybe. What happens to these atoms which are in this lattice vibrating? What happens to these atoms when we start to heat the substance up? Good. When we raise the temperature, we actually said in the comments, raising the temperature is like raising the kinetic energy of the things inside the substance. So these things are still fixed where they are, but increasing their kinetic energy means they're going to be vibrating a bit harder and a bit faster. Good. So atoms gain kinetic energy, so vibrate faster. Good, really nice answers in the chat as well. Perfect. All right, so the second half, there's a bit more conceptual stuff, but also there's going to be a couple of formulas now describing how easily things change state and how easily things change temperature. It turns out that both of those things are material properties, and I'll explain that what that means when we get there. It's a small change in kinetic energy, so they will vibrate more, but to a smaller extent. Yeah, really nice. All right. So now we're going to think even more about increasing temperature and the changes of state as things heat up. So when I take a substance, let's imagine, for example, I start with some ice. So I've got some ice, okay. And then let's assume I constantly heat it. So here's my block of ice, and maybe it's in a container, and I just put a flame underneath it so that it's constantly receiving more and more heat energy over time. So when it's constantly heated, its temperature will rise as particles gain kinetic energy. So we've got these particles, it's ice, it's a solid, so they're in a fixed lattice. And as the ice gets heated, they start vibrating faster and faster and faster. Now, so at the moment, it's not melting. They're just vibrating faster and faster. So as a result, over time, more and more heat gets put in. Heat put in over time. So each time interval I wait, a bit more heat comes in from the flame. And as a result, the temperature goes up. More heat gets put in, particles in the ice move faster and faster. But then something weird happens in this graph, and we're going to explain what happens. There is a certain temperature we can reach, this temperature here. Maybe someone can try and guess what this temperature would be. And at this temperature, the temperature stops rising. Even though we're putting heat in, even though we're heating up, yeah, you're right, this is going to be 0 degrees centigrade, and we're going to explain why that is now. So at certain temperatures, the temperature stops rising. So where's this energy going? Temperature was kinetic energy. We're putting energy into the ice. So if it were going into the kinetic energy of the particles, the temperature would be rising. So where's the energy going? I'm putting energy in, but the temperature isn't going up. Where's this energy going that I'm putting in? Absolutely right, nice. The ice has internal energy overall, which is kinetic plus potential. So if I tell you I'm putting more energy into it, so I'm increasing its internal energy, and you tell me, well, the temperature's flat, so the kinetic energy isn't going up. It must be the potential energy that's going up. So what does that mean? Exactly. Increasing your potential energy, we said, is what breaking bonds is. So here, the energy goes into breaking bonds. Okay, great. So we've got all this heat going in, the temperature doesn't go up, but the potential energy is going up instead. So what's happened here? Well, here we've broken all the bonds. So here, what state are we in? We've broken all the bonds that were keeping us in a lattice. That's what increasing that potential energy was. So now we've broken all the bonds. It's not being held together as a lattice. We have a liquid. Here it would be liquid water. Really nice, yeah. So from here on, what happens? Well, we start putting heat in and the liquid gets hotter and hotter and hotter until what's happening here? So this was melting. Let's call this A. What's happening at B? If A is melting, what is B? At B, we've increased the temperature of a liquid and suddenly the liquid's kinetic energy isn't increasing anymore. Yeah, it's evaporating or boiling. Nice. Boiling. Good. That's really wonderful. Nice one. Okay. So now we're going to do the maths. So specific heat capacity of a substance is essentially a measure of how easily its temperature increases. So it's given the symbol C. And this is like saying yeah, so it's really, I've got a substance, I've got a material. How easy is it for me to heat up? In other words, how much energy do I have to put in to increase its temperature? Okay, so specific heat capacity is the heat energy per unit mass required to raise temperature by 1 Kelvin, which is the same for the record as raising by 1 degree. Good, okay. So there's a formula which involves the specific heat capacity, and it's the following formula, which is actually a direct translation of the definition in words. So the formula says the change in energy of a substance is given by taking its mass, multiplying by its specific heat capacity, and then multiplying by your change in temperature. So the mass here is going to be in kilograms. Change in energy here is going to be in joules. Change in temperature is going to be in kelvins or degrees. And then the specific heat capacity you can figure out from this is given by, well, C equals delta E over M delta theta, which is change in temperature. So we've got joules per kilogram per Kelvin. Joules, kilogram minus 1, Kelvin minus 1. Perfect, okay. And you can actually see in this formula here, where I've just rearranged that formula, that it kind of says what the sentence does. The specific heat capacity, that's this thing here, is the kind of heat energy per mass, so heat on the top, per mass, required to raise temperature. So that's kind of like per temperature. All right, let's do a question. Calculate the temperature of 500 grams of water at 23 degrees centigrade after 36 kilojoules of heat is applied to it. The specific heat capacity is so much. Usually with these specific heat capacity ones, and we'll see with the changing state ones as well, it tends to be a lot of numbers in the question. So it's worth giving these symbols straight away. We know the mass. Mass is 500, or let's convert into the right units, 0.5 kilograms. Okay, we know a temperature, we'll come back to that. We know how much heat is supplied. Now, heat supplied was this delta E symbol. Delta E is change in energy or heat supplied. And that is 36 times 10 to the 3 joules, just converting units. And we know C. C is 4200 joules, kilogram minus 1, Kelvin minus 1. Okay, so we've got everything in the right units. And the only thing we don't have from this formula is change in temperature. So that's great. Yes, I think you're right, actually, yeah. So let's rearrange this formula for the change in temperature. Change in temperature is equal to heat supplied divided by mass times specific heat capacity. So we can chuck this into a calculator and we'll get 36 times 10 to the power 3 divided by 0.5 times by 4,200. Okay, putting that into a calculator should give you around 17.1428, etc., etc. Okay, so that's the change in temperature. It's got to be an increase in temperature because we put heat in. And we started at 23. So altogether, the kind of new temperature is equal to 23 plus 17.1428, etc., which is indeed roughly equal to 40.1 degrees centigrade. Really nice. All right, so that was the formula that we used to talk about change of temperature of a material. Now we'll look at the formula that we use to talk about the change of state of a material. So specific latent heat of fusion or vaporization of a substance is the heat required to change state without changing temperature. Okay, and I should mention here it's the heat required per mass. So, okay, the specific latent heat is the energy we have to put in per mass. Aha, so one way of thinking about this is the energy that we have to put in to change a certain mass from one state to another is given by multiplying that mass by the specific latent heat. Is it centigrade or Celsius? Aha, that's a good question. So the change in temperature you can think of as being either Kelvin or degrees Celsius. It doesn't matter because it's a change. The change is 17.1 Kelvin or 17.1 Celsius. Now we started with 23 degrees Celsius, so we can just add this change to it to get another temperature in degrees Celsius. Let me know if there's any more questions about that. Okay, so using the same kind of analysis as before, specific latent heat has units of joules, that's energy per kilogram. Let's have a go at a question. And this is quite a nice question because it involves specific heat capacities and latent heats. Calculate the temperature of 170 grams of water at the boiling point after 420 kilojoules of heat is supplied to it. Okay, we've got a certain amount of water at the point is a liquid. Maybe we should draw the bit of graph that we're on here. We're at the bit where we're a liquid and we're going to change state to become gas. And then after that, we're going to increase our energy again. So liquid, water, that's where we're starting. Here we get to steam, and then we would just raise the temperature. Here's our graph of temperature against heat in. Good, okay. The specific heat capacity is so much, and the specific latent heat is so much. Okay, so here's the technique here. We have a certain amount of water, and we're going to put in a load of heat. It turns out the amount of heat that we put in is going to take us past just boiling all the water. So some of that energy, this much if you like, will go into boiling the water, and then we'll have some left over. And if we can figure out what we have left over, we can use the specific heat capacity to find out what the change in temperature will be due to that extra bit of heat. So first of all, let's figure out how much energy it takes to boil this liquid. So we know the energy required to boil is going to be equal to the mass of the water, which is 170 times 10 to the minus 3 kilograms, multiplied by the specific latent heat. So we're using this formula here. And the latent heat for vaporization is 2.3 times 10 to the 6 joules per kilogram. So you can chuck that into a calculator. And I'll do that here actually, just to save space. And that should give you 391 times 10 to the 3 joules. So now we ask ourselves a question. If that's how many joules we needed to change the state, then whatever we have left from the energy we put in, that'll go into increasing the temperature. And they want to know what the final temperature is. So what's left? The remaining energy that we can put in is the 420 that we can put in overall, minus the energy that we wasted boiling this thing, which was 391 times 10 to the 3. So altogether, that'll give you 29 times 10 to the 3. And that's the energy that we have left that can go into changing the temperature. So now we use a specific heat capacity formula, delta E equals mc change in temperature, and we rearrange for change in temperature, which is delta E over mc, which is 29 times 10 to the 3, divided by m, which is, well, we still have this much water, it's just that it's all steam now. So 170 times 10 to the minus 3, multiplied by c, which is this number here, specific heat capacity, which is 223. Good. And now we can chuck that into a calculator, and we'll find that we get around 15 degrees. Now, all we need to know is what temperature we started with. We know the change in temperature is going to be 15. So what did we start with? Well, we started with water vapor that has just boiled. So we were starting here at 100 degrees. Therefore, the final temperature is equal to 100 plus 15, which is 115 degrees centigrade. And that's the final answer. So it's a really nice question. It's quite an involved one, which gets you to use actually both the formulas that we learned there. Okay, so how's everyone feeling? Does anyone have any questions? Feel free to let me know if there's anything you're feeling confused about. You're kind of confused. Okay. What is good is the next question we're going to do is going to be another one of these ones where we combine talking about latent heat and heat capacity. Yeah, sure. So what do we do? 420. Let me go back to here. So imagine this scale here is heat that we're putting in. We started off here, and we're going to put in 420 times 10 to the 3 joules. And they want to know what temperature our liquid is going to end up at. Now, our temperature started at 100 degrees centigrade because we had water at its boiling point. So we started at 100 degrees centigrade, and we wanted to know what temperature we're going to end up at when we put in 420 times 10 to the 3 joules. So this is the thing we want to find out. Okay, so we can do this in 2 steps. We need to know how much energy went into heating up the substance. Whatever this bit is here, let's call that delta E. That's the energy that went into heating the substance. So there we can use the specific heat capacity formula to find this change in temperature. So all we need to know is how much energy we wasted on actually boiling the liquid before we could get to this point here where we start putting energy into increasing the temperature. Now we found out that this was 391 joules. That's how many joules we needed. As a result, what we had left here to put in was around 29 times 10 to the 3 joules. So then we used that energy that we knew we were going to put in to find out what the change in temperature would be because of that energy we put in. And that was given by using delta E equals mc delta theta, where this was the energy that we were putting in. Does that help at all? We're putting in a load of energy. Some of it goes into a changing state. We find out what's left, and from the energy that's left over, we can figure out what change in temperature it's going to cause. It is kind of a confusing one because there's these like 2 steps to it. We do have another question we can look at. So maybe this will help. But let me know if you have any other questions. When I get 15, you tried it, but it came up as 85. Oh, okay. That's interesting because that's 100 minus 15. I will very quickly recheck the calculation. Just do that. Uh-huh. 29 over 170 over 2000. Interesting. Yeah, I also get 85 degrees. My apologies. So that changes one thing. That just changes the very final answer. So apologies for that. You're absolutely right. This is about 85 degrees. So the final temperature is 100 plus that, which would be 185 degrees. Is that all good? So you're absolutely right if you got 85. Okay, sweet. All right, let's have a go at another question. Molten lead at its melting temperature of 327 degrees. Okay, sweet. Awesome. Sorry about the mistake. Molten lead at its molten temperature of 327 degrees is poured into an iron mold where it solidifies. So let's draw a picture. We've got this iron mold and we've got the molten lead, which has been poured into it. Okay. And this is at 327. Good. The temperature of the iron mold rises from 27 degrees. So it starts off at 27 and it ends up at 84, at which point the mold is in thermal equilibrium with the now solid lead. Okay. So this is like the after sitch. Afterwards, we've got iron. Now it's at 84 degrees and it's in equilibrium with solid lead. So we've got the lead here, which is now solid. And because it's in thermal equilibrium, well, it must have the same temperature. So we've managed to harvest all the information they gave us into two diagrams, the before and the after. Okay. And then we're given a load of extra numbers. We're asked to calculate the heat energy absorbed by the iron mold. So the iron mold is this outside thing. And the first question is, did it change state? It did not change state. It started as some kind of solid and its temperature just increased, but it remained solid. It's still an iron mold. So what's the change in temperature? Well, we can figure that out. And so we can use that to find the heat energy. So the heat that went into the iron mold is given by its mass times its specific heat capacity times its change in temperature. So that's going to be given by, well, the mass is 3 kilograms for the iron. That's here. Specific heat capacity of iron is this, 440. And then we just have to multiply by the change in temperature, which is 84 minus 27. So we can chuck that into a calculator and you should get 75240 joules, which is roughly 75200 joules. Great. Okay. So we know how much energy was transferred to the iron. Now, maybe it's worth thinking to yourself at this point, where did that energy come from? Well, we're not assuming there's anything else really going on. So what that means is the lead gave the iron heated up by this much, that required this much energy. So that must be the energy that the lead gave to the iron, because the lead cooled down. It was really hot and it was liquid and it cooled down and heated the iron around it. So in fact, this is the energy that the lead lost. It lost that energy and gave it to the iron. Okay. Calculate the heat energy given out by the lead while it's changing state. Okay. Well, do we know how much of it is? There was. We know the lead had a mass of 1.2 kilograms. And we know the latent heat. So we know everything we need to find out the change in energy when that much lead changes its state by that much. The change in energy here is equal to M times L, which is 1.2 times the specific latent heat of fusion, which is 2.5 times 10 to the power 4. So you can chuck that into a calculator and you should get 3,600 joules. Not 3,000, 30,600 joules. Let's just check that. Sorry, that's a typo. This is just 30,000 joules. There we go. Okay, good. So, next part of the question. Calculate the specific heat capacity of lead. Yeah, I got 30,000. Yeah, nice. Okay, so we want to calculate specific heat capacity. And maybe the first thing we should do is write down the formula that has it in. We know delta E equals MC delta theta. So if we want specific heat capacity, that's C equals delta E over M delta theta. Now we need to figure out what numbers all these things in this formula should be. So the specific heat capacity, that's all about the change in temperature of the lead. So there was really 3 stages. We had the lead, it was liquid. Then we had the lead and it was solid. It started at 327. Now it's still at 327 because all the energy it lost went into just changing its state. And then finally, it cooled down to 84. Now we know how much energy it gave out overall because we calculated this. The energy given out overall was 75200. 5200. And we know the energy given out in this melting period here, in this, becoming solid part here, because that's here. The heat energy given out while it's changing state was 30,000. So this part here was 30,000. So the change in energy whilst it was changing its temperature is whatever remains. It lost this much overall, but we take away this bit. So the delta E is 75200 minus 30000 divided by 1.2 times the change in temperature, which is 327 minus 84 degrees. You can chuck that into a calculator and you'll get 155 joules per kilogram per Kelvin. Okay, and one reason why this is only an approximation is some energy would actually be lost to the surroundings. Okay, so there was a final question, but I kind of have to wrap up, partly because I have to give 2 more sessions. Well, I'm getting ready to give 2 more sessions actually on the SnapRevise website. So let me just check the, yeah, okay. So we're actually gonna wrap it up there. And because I just have a couple of things to go through and mention at the end as well. So thanks very much, everyone, for coming to the session. And thanks for asking various questions. And thanks very much for saying when you're confused, because it's great. It means, you know, when we know when to go back and clarify things. So you should now be able to define internal energy. That was a key thing today. You should be able to understand the Kelvin temperature scale in absolute 0. And you should be able to calculate and describe changes to a substance when it's heated. So this was all about specific heat capacity and specific latent heat. So do let me know if you have any questions. In the meantime, there's some stuff to let you know about. We're doing all sorts of stuff now, especially because terms just started and we're all starting new courses. So let me know in the chat if you have any questions about the material. In the meantime, there's a load of web classes coming up, just like this one on YouTube, so absolutely check these out. We're doing biology, a couple of maths, and a chemistry. And also, if you go on the SnapRevise website and you have a code for this, which we had at the start, but I'll mention again here as well, you have 25% off of the SnapRevise courses, the courses on the SnapRevise website. And there's all sorts of things going on there. So it'd be really great to see you there on the website. So we've got loads of like pre-recorded videos, which are just like courses. So it's like we've gone through the entire specification for the 3 main exam boards and just converted the idea of a textbook into essentially a video textbook. So we teach you all these concepts from scratch. It really is a course, not just revision. So then we're doing a bit of smart learning as well. So at the start and end of each part of the course you do, there are various quizzes you can take. And rather than just letting you know how you did, so you can decide what to do next, actually the various bits of the course and various videos will become highlighted after you take the test as the important things that you in particular need to work on. So the idea is to kind of try and streamline your work and make sure that you kind of study smart. Okay, so we've also been putting together revision guides in case you prefer reading. We've been doing some walkthroughs where we show you how we would try and answer various exam questions. So we take you through step by step how we extract the information from the question and then how we construct our answers, especially on the longer form answers. And we've been coming up with our own sample exam questions that you can practice as well. So I'm going to show you a bit of that on the SnapRevise website now so that you can see how this stuff looks. And also, we're doing web classes where we do sessions like what we did today, but there's actually quite a few of them on each week at the moment. I think there's 5 physics ones a week now that term has started back up. So I'm going to go in a SnapRevise. 1 second. It's asking me to join our course there. Okay, so I'm on the SnapRevise website and I'm lucky enough to be added to some courses right now. So whenever I want, I can go onto the physics course. And then right now there's some web classes live, which you can go and take a look at, but there's also the course itself. And actually, for example, if I go into year 13, there's a load of quizzes I can take on thermal physics. So let's take the one on specific heat capacity and latent heat to see how it works out. Well, I'm just going to guess some answers, but this is to test your knowledge at the start before you even get going with the course. And once we finish the answers, the course will then be tailored towards us. Nice. So I'm getting a couple right here by pure chance. That's the last one. Last one. Ah, there's a few more. Okay. So just absolutely smashing through these. I think the website is probably going to think that there's a lot I have to work on here, which is fair enough. Okay. So once I've gotten through all the questions, okay, 8%. So not my best run. Tells me what I know and what I don't. But then when I actually go into the course, the videos with parts that I need to look at are highlighted in orange. And even then, within the videos, I can go to the particular parts which are highlighted in orange. So this is all about trying to kind of streamline your learning. Okay, so thanks very much for coming along to the session. was really great. It was really nice and interactive. So thanks very much for all your input. And in the meantime, I will just remind you of the code that we have. So here we are. 1 second. Here we go. So here's the codes. It's got 48 hours. So yeah, thank you very much for coming. Thanks very much for keeping the session interactive, and hopefully see some of you on the website. And either way, see you all at the next YouTube session. All right, cheers for coming, everyone. Okay, bye.